Well, good morning, everyone. I'd like to begin by thanking the organising committee for inviting me to come to talk to you. It's been a great pleasure. I would also like to thank all the student helpers who have made my time here very happy and been very helpful. My talk is going to be in two parts. One about the foundations of the periodic table, and another about elaborations, extensions of the periodic table. Unlike most people who have spoken so far, who have thought that 100% of what they were saying was useful, I will admit from the beginning that only 1/3 of what I'm going to talk about is useful. That is, the foundations. The elaborations are going to be completely useless, so don't bother to watch the second part of my presentation. It's really just a way of filling in my 50 minutes. Some years ago, I wrote a book called The Periodic Kingdom, where I treated the periodic table as a country to visit. And so I could talk about the discovery of the country. I could talk about the mapping of the country. And I could talk about the laws and administration of the country. What I'd like to do today is to turn the periodic table over and look underneath it to see the mechanism by which drives the periodic table. And in the process of doing that, I will come to explain why I have chosen this image as on the title page of my talk. I actually came across it in a magazine in England only last week. It's an advertisement of a jeweler trying to sell this object. But you will see in a few minutes that this image, this helix, the spiral, is actually a deep underlying feature of the periodic table. Don't worry if you don't see the point yet. I hope that in the useful part of my talk, you will come to see what I mean. And the mechanism that I will talk about mostly today is symmetry. So I will talk about the way that symmetry guides our understanding of the periodic table and is responsible for most aspects, most deep aspects of its structure. And I'll begin with the Coulomb potential. And here is a representation of the Coulomb potential with which you are all familiar. This is a very special potential, and you'll see why very soon. I think if I were God, who knows, I might be, if I were God and I wanted to give an electrical potential to the world, to mankind, of the most beautiful kind, I would give the Coulomb potential. And you'll see why very soon. Because when you solve it, as everyone here who has started any chemistry at all knows, that you end up with an array of energy levels, which I've drawn here. And this is always the starting point for people talking about the structure of the periodic table, using the Aufbau principle, penetration and shielding, and so on. So there is the beginning of the explanation of the periodic table. And what you get, of course, is if you just stayed with the structure that I have just shown and did not take into account electron repulsions, you will get a very primitive periodic table. There is something very peculiar about the hydrogen atom and the periodic table, which everyone is aware of, but people find it very difficult to understand, which is why there are exact degeneracies, why an s orbital has the same energy as a p orbital, likewise 3d, likewise 4d, 4f, 4p, 4s. How can we understand the exact energies, equivalent energies of those collections of orbitals? It's easy to understand, of course, why the p orbitals have the same energy, because we have a p orbital like that, and a p orbital like that, and a p orbital like that, and suddenly we have a 2s orbital like that. Always, whenever you find an exact degeneracy, you can rotate this into that, into that. But this one seems peculiar. How can you rotate an orbital of this shape into an orbital of that shape? Well, the answer lies in thinking in 4 dimensions. So I'm going to help you think in 4 dimensions, to see that when you step into 4 dimensions, you can rotate all 4 orbitals into each other. So necessarily they are degenerate. In 3 dimensions, of course, it's easy to understand, because you can take this arrangement in which I've inscribed the Coulomb potential inside a cube. I can rotate it and get something like that. I can rotate it in another direction and get something like that. So you can see that you can rotate px, py, pz easily into each other. But you can do the same thing in 4 dimensions. Now, various people have made attempts at depicting 4 dimensions. I think one of the most celebrated is shapes like this, which have been developed by artists. In fact, there is an image by Salvador Dali, who perhaps was also trying to explain the degeneracy of the hydrogen atom. I don't think I don't think Jesus helped him very much, so I'll get rid of him like that. But a structure like this, when you can rotate, when you can fold up that structure into a hypercube, then you do display the 4 dimensions, 4-dimensional symmetry of the Coulomb potential. But that's too hard. So let me step down a dimension and say, well, how do we can rotate a 2-dimensional object into this 2-dimensional object very easily. But how can we rotate this object into that object? I'm working here in 2 dimensions. And the analogy of showing the 4-dimensional symmetry of the Coulomb potential is to step up a dimension into 3 dimensions. So let me depict these shapes now as projections of this coloured sphere. And you can now see that I can certainly rotate it into that. So I go from a shape like this to another shape like this, or I can rotate it by another axis. So in fact, I can rotate the 3-dimensional sphere projected onto 2 dimensions, and you immediately see that you can rotate this structure into that structure and to that structure. So stepping up a dimension enables you to understand the degeneracy of the hydrogen atom. The Coulomb potential, as I said, is symmetrical in 3 dimensions, and the amazing thing is that it is also totally symmetrical in 4 dimensions. So by analogy, you can begin to see how those degeneracies arise. And you can take other shapes. how do you rotate this shape into that shape? You can play with shapes like this to see what is happening. And of course, if you have a sphere which is coloured like that and project it onto the plane, then you can rotate it around different axes, and the projections are rotated into each other. There's some more. Now, at this stage, with the pure hydrogen atom, we have this very simple periodic table. But we know that in fact, when you have more than, when you've got only one electron, it experiences this pure Coulomb potential, this four-dimensional potential. But if you have two electrons, then you have an additional source of electric potential, and you get symmetry breaking. You've lost the pure symmetry arising from the central nuclear charge, and suddenly you have got a very complicated system. And of course, we all know that when we take that into account, then because of symmetry breaking, the periodic table itself emerges as a structure like that. We've talked for hours today, over the last 2.5 days about that, and I won't say much more about it. Let me ask another question. Where does the Coulomb potential come from? How can you understand the origin of the Coulomb potential, which of course underlies the entire structure of the periodic table and of what I'm speaking about? Well, we need to go back, first of all, to 1927 and to look at different aspects of symmetry. Back in those days, before 1927, an electron looked like that. After 1927, of course, when it was realized that electrons had wave properties, an electron stopped looking like that and began to look like that. And there is my helix. You normally say, well, a wave is something that does that. But in fact, that's not correct in quantum mechanics. A wave is something that is helical, and the sense of twist gives you the sense of motion of the particle. So here is actually a representation of an electron moving across from left to right. It's a helix. And those of you who are not quantum mechanically knowledgeable, all you need to know about quantum mechanics at this point is that the radius of this helix tells you the probability that a particle is present. So if I have that as my helix, the particle moving in this direction, then there is the radius, and it is probable that you will find the particle here. If it's that, you have it's still moving in this direction, but you have a lower probability of finding the particle. If it looks like that, then there is no probability at all of finding the particle. So that's all you need to know about the interpretation of quantum mechanics at this point. Now, there's another symmetry that you need to be aware of, and this is so-called gauge symmetry. Gauge symmetry is the foundation of modern theories of forces. And I will teach you just a tiny little bit of gauge theory. First of all, what is a gauge? Well, it's a measuring rod. And so gauge theories in physics, now in chemistry, are all about measuring rods. And you can see that I could take this helix, this particle moving here, with a certain probability of being found here, and I can move the wave along. And I've represented it here. So I've changed the gauge, as it were. I've moved the measuring rod from the blue position to the yellow position. And you can see that although there is a change of phase, there is no change of radius. So there is no change in physics. If the electron would be found here with a certain probability when the wave was blue, it will be found here with the same probability when the wave is yellow. That is, physics is gauge invariant. So I'm talking about, the symmetry I'm talking about is gauge invariance. And those of you who look at modern theories of fundamental forces will discover the term gauge invariance. And all it means is that the physics remains the same when you move the wave along a little bit. But you can see that, suppose I were to consider a region of space, and I were to change the gauge, I were to change from blue to yellow. What flows into this region of space is identical to what flows out of this region of space through the opposite face. In other words, there is no change in probability of finding the particle inside the box. What flows in is matched by what flows out. So this is so-called global gauge invariance because you're moving the entire wave and it passes into this region and out of this region. And the implication of that is that, think of this as representing an electron. There is no change in the electric charge inside this region. So in other words, global gauge invariance, this obvious symmetry, implies the conservation of electric charge. And although it's never mentioned, of course, that is fundamental to the existence of the periodic table, because it means that electrons do not lose their charge. They have constant electric charge. The proton has constant electric charge. There is no charge. The atom does not decay because the electric charges of the electrons and protons gradually disappears or gradually increases. It's through global gauge invariance, this very abstract symmetry, that atoms exist. Now, back to this wave again. This wave satisfies the Schrödinger equation. And this is the Schrödinger equation in as much detail as I think it is necessary to show you. So there is the Schrödinger equation. Those of you who want more details can imagine what is inside this box if you want to. But this wave satisfies it. This yellow wave also satisfies it. No problem. But now let me do something which is more subtle. Let me take the blue wave and change the wave to yellow by different shifts, but at different points. So there is a big shift from here to here, but only a tiny shift from here to here. Okay. Still the physics remains the same. There's no change in amplitude of the wave, so there's no change in whether an electron would be found somewhere. The physics, what we observe, remains exactly the same. So this is called local gauge invariance. And the consequence is that the Schrödinger equation no longer, the yellow curve is no longer a solution of the Schrödinger equation. The blue wave was, but by shifting by different amounts locally, we no longer, the yellow wave no longer satisfies the Schrödinger equation. We need a new equation which is the Schrödinger equation, with an extra bit. And the extra bit, quite extraordinarily, are the Maxwell equations. So, or consequences of the Maxwell equations. So in other words, local gauge invariance implies the existence of electromagnetism. So you can then see the very deep origins of what holds atoms together is this thing called local gauge invariance. And a consequence of that, of course, is the Coulomb potential. So out of symmetry, we have got the glue that holds atoms together, and indeed the laws, all the laws of electromagnetism as discovered by Michael Faraday. And you can see that really the world is a manifestation of local gauge invariance, as indeed atoms are as well. Now I've talked about 3 dimensions. I have also mentioned 4 dimensions. And it is obviously natural to think, therefore, about other dimensions, like 2 dimensions and 1 dimension. And let me warn you, this is where the totally useless part of my talk begins. So don't worry about what I'm going to say from now on. It is completely useless. It's an intellectual game, and I think it's quite fun to have intellectual games. I think, indeed, almost everything useful about the periodic table has been said over these past 2 days. So I think I now have a license to say useless things, because everything that can be said has been said that is useful. Apart from, of course, the lectures that will follow me. So let me think about what the periodic table, if we lived in flatland, so that is, if the world were 2 dimensions, what would it look like? We know what it looks like in 3 dimensions, although of course there is no agreement even on that, as we have seen several times. I want to explore in a very naive way what it would look like in 2 dimensions. So I'll go back to the hydrogen atom and then do what we do in 3 dimensions to the hydrogen atom, but I will do it in 2 dimensions and see where it leads us. The question though is, what is the Coulomb potential in flatland? What is the Coulomb potential in 2 dimensions? Well, by arguments that I would be happy to take you through, but I will not go through at the moment. In 2 dimensions, the Coulomb potential is a logarithmic function of the radius. No longer 1 upon r, now the logarithm of r. And so it's still spherically symmetrical, but the radial dependence is like that. Certain complications there. One is, it's rather difficult to solve the Schrödinger equation with this potential, but you can cheat. And the way that I would like to cheat is to say, well, the blue line is the actual potential, Coulomb potential in 2 dimensions, and it gives you this surface, blue surface. The ordinary potential goes as 1 upon r, which is this yellow shape. And it would not be too wrong to say, well, let's use the usual Coulomb potential in 2 dimensions and not try to solve the Schrödinger equation with this awkward logarithmic term. And the great advantage of that is that you can solve the Schrödinger equation analytically in 2 dimensions with this 1 upon r potential. And the solutions that you get are like this. These are the value of the angular momentum and its projection. This is the equivalent of an s orbital in 2 dimensions. These are all s-type orbitals. These are p orbitals, and these are d orbitals. So you can see that you can solve the equation and get all the structure that you need. You can, of course, also get all the energy levels in 2 dimensions. They have a very simple form if you take the ordinary Coulomb potential and use it. They just have this dependence upon the 2 quantum numbers n and ml. And that is the expression that you get. So sophisticated about penetration and shielding and so on. Out comes a periodic table. So if we lived in a 2-dimensional world, then this would be the beginning of the structure of the periodic table. So this is you can see that it's got resemblances to the 3-dimensional one, but you've got strange bedfellows. Suppose we did it in 1 dimension. What would the periodic table look like if we lived in lineland? Which is, so we simply have 1 line that we inhabit. Once again, the question is, what is the Coulomb potential in 1 dimension? And by arguments that I could also go into if you wanted, the Coulomb potential in 1 dimension is simply R itself. It goes linearly from this value, linearly up forever. That's the Coulomb potential in 1 dimension. And so what we're now looking at is an electron confined to a V-shaped potential trough. And that can be solved. I mean, I solved that equation fairly straightforwardly, and you get a series of energy levels and the corresponding probability distributions. So you can now see that these are the actual energies in some sort of units, never mind what the units are, but you now have a complete solution for a hydrogen atom in 1 dimension. And you can see that out of that comes a periodic table, which consists, for the first 6 elements anyway, of something like that. So there is the very boring periodic table for a hydrogen atom that can exist only in 1 dimension. You can actually also solve it exactly for the conventional Coulomb potential in 1 dimension. And these, very interestingly, you get very simple expressions for the energy. And of course you get these different wave functions, which resemble the ones that I've just talked about, the exact ones. And so once again, you've got a periodic table that emerges simply from the Aufbau principle. This just goes on forever for whatever 1/2 of 818 is. What's another symmetry that we could employ? Well, we could turn atoms inside out. And so instead of having a nucleus with an electron surrounding it, we could take away the nucleus and just have a well. Okay? So is there a periodic table of electrons in wells of various dimensions? And here is the other solutions in 2 dimensions, which can be found analytically. And these are the probability distributions. So you have an S set, you have a P set, a D set, and an F set, and so on. So that is what the inverse atoms would look like. And the energy levels, of course, as I've shown, can be filled in the usual way. There's no penetration and shielding effects to consider because there is no nucleus anymore. So it's just inside a cavity. But the periodic table that emerges from that is this one, with all sorts of short four-member groups, blocks. And I've just labelled them SPDF, depending upon the quantum number ML. And inverse atoms in 3 dimensions. I mean, take away the nucleus actually of an atom in 3 dimensions. So what you've got is a spherical cavity with an electron inside that cavity. Once again, this is a standard solution that, of the Schrödinger equation, and we can develop the energy levels again. And so these are some of the solutions, and I've just done 3s, 3p, 3d to show you how some of the solutions would look. These are the probability distributions. We were talking over lunch yesterday about the shape of H orbitals, and so let me show some H orbitals as well. These are the set of orbitals characterized by quantum number L equals 5, and the various components. So you can begin to see that these are the electron distributions. Once again, one's got energy levels which can be evaluated analytically, and these fall into groups. These fall into groups, depending upon the angular momentum quantum number, 0, 1, 2, 3, 4, 5, and so on. And so once again, you can use this as a basis for a hydrogen, for a periodic table. And so a periodic table for electrons in 3-dimensional cavities, which is possibly a real arrangement, might relate to the superatoms that we were talking about the other day. This would be the shape, crudely speaking, of the periodic table for such systems. Those were largely useless components of my talk. In the remaining 5 minutes or so of my presentation, I'd like to talk about completely useless material, which is almost useless beyond your imagination. Seriously useless. That is, where does the periodic table end? This has been touched on, and we know a little about where what's going to go on maybe in the next period as all these groups around the world struggle to get that next Nobel Prize and call it whatever it will be called. The periodic table, by it I mean the periodic table, what goes on down here? Let's not be pusillanimous. Let's not be feeble-minded. Let's be bold and go where man is never likely to go. And see what happens when we get to somewhere like element 10,000. So when we come back here and celebrate Mendeleev 150,000 years, then we might have got down here. And there is the general shape of the periodic table into this world of fantasy. And I've taken you all the way down from past G blocks through H blocks, J, K, L, M, N blocks. So we're down in the thousands, where, of course, well, it takes you down to this is the atomic number, which I think all of us agree will take a few years to get to, since we're only up there. But the problem about this, I mean, the underlying problem now is yet another symmetry. And that other symmetry is going to work against us. And this is the symmetry of space and time. Put another way, it's the role of relativity, washing out the structure of this table. We're already alert to the possibility that relativity is important up here, might wash away the block structure even at this point. And so all this is kind of washed away chemistry, and it will not be possible to pursue so-called periodic laws into this region. Let me just present an argument which might be the same as the one that Packer didn't present yesterday, but alluded to. But you'll tell me whether it is the same. It might be a little bit different. So relativity is important when the speeds of electrons become close to the speed of light. What value of the atomic number is there at which this becomes important? Let's think of the hydrogen atom again. But I will talk about the hydrogen atom energy level, its total energy. This might be an unfamiliar way of writing its energy, but I have used the fine structure constant to put it into this expression. And there's the mass of the electron, the speed of light, and the atomic number. This is just the usual Schrödinger formula for the energy, but written in terms of the fine structure constant. The fine structure constant, in case you're not familiar with it, the name is silly. It should not be called the fine structure constant. The name should be something like the electromagnetic coupling constant, because alpha, which has the value of 1 divided by 137, is a measure of the strength by which a charge couples to the surrounding electromagnetic field. And you can understand why this formula is valid, because think of the structure of a hydrogen atom as a proton generating a photon, and it will do that with strength alpha, throwing the photon towards the electron, and the electron catching it. So they are bound together by the interaction conveyed by a photon. And the strength with which the electron can catch the photon is also alpha. So you can see that the energy should be something like, be proportional to the square of the so-called fine structure constant, proportional to 1 upon 137 squared. There is the energy of the hydrogen atom. Oh, sorry, the proton, or the nucleus, throws off a photon with a probability Z times alpha. The electron catches the photon with a strength alpha. There's still one more Z to account for, and that is the closeness of the electron to the proton. So as the nuclear charge increases, the photon does not have so far to travel. So you can begin to understand that this reveals in a very deep way the energy level of a hydrogen atom. But I'm going to concentrate on alpha and Z. And here is the total energy. The well-known theorem, the virial theorem, says that this total energy consists of a potential energy, which is twice the value of that, and the kinetic energy, which is the same value as this except for the sign. So you can see that the potential energy plus the kinetic energy is the total energy. And that's where that formula is. But the kinetic energy is that expression. And classically, the kinetic energy is 1/2 mv squared. So I can now relate v squared to alpha squared and z, and find that v squared is just that quantity. And therefore, v itself is approximately the fine structure constant times the speed of light times z. So all we need to do now is to think, well, when does this quantity here, when does alpha z approach 1 so that v approaches c? So if we write z is equal to kappa upon alpha, then z is about that. Now, space rotates into time as the speed increases to the speed of light. It reaches halfway, so kappa, the space is half turned into time when the speed of light, when the speed is 1/2 the speed of light. And so if we took kappa to be about 1/2, then it means that relativity becomes important at half this 137, which of course is exactly where we find it. So on this sort of argument, you can predict that everything I said about that, although nonsense originally, is even more nonsense because of the effect of relativity. Anyway, I'm going to stop there because my time, I think, is exactly up. But let me just put up a final image which brings us snake-like back to the first slide that I showed. I think the lesson to draw may be from the uselessness of most of my talk is that the periodic table is immensely stimulating. We have seen it stimulating all kinds of contributions over this past 2 days. It's sort of stimulated my own 2/3 at least useless contribution today. And the periodic table, amazingly, it goes back to a single piece of jewellery, and indeed is itself a jewel in our cultural history. Thank you very much.